Hi everyone, this video is part of Macquarie University's coding tutorials, and today we'll provide an introduction to recursion exploring its mathematical foundation. Through a real-life analogy of work delegation in organizations, we'll understand the benefits of using recursion to solve complex problems in a more efficient way. So, what is recursion? Recursion is a method of solving a problem by dividing it into smaller subproblems, solving those subproblems, and finally, consolidating or joining the solutions to those subproblems to get the solution of the original main problem. This is a repetitive process, and currently we've only been using for loops and while loops. However, we will eventually come across problems that include branching, so that at each subproblem there are multiple other problems to solve. This means that the chain of execution can look more like a tree rather than a linear repetitive process, which is what we get with loops. Let's see what this means by using an analogy. One way to think about recursion is through work delegation in organizations. Assume you're the CEO of a company with a task that needs to be completed. You could try do it all yourself, but that would be inefficient and time consuming. You could instead delegate the task to one of your managers. However, that manager may not have all of the necessary skills or resources to complete the task alone. As a result, they delegate the task to one of their employees, and so on until the task is completed by someone with the necessary skills and resources. The structure could look like this with a direct chain of command and is what we would typically associate with loops, although basic recursive solutions can also allow for this sort of pattern. Or we could have multiple staff at different levels who must complete their own tasks, and their manager must wait until all of their employees' tasks are completed. This simulates the tree approach with branching that we talked about earlier. Only once all of the employees' tasks are completed can the manager solve their own task. In all cases, whether linear or branching, as soon as the relevant employee completes their smaller task, they will notify their manager. The manager will then add what they can to the task and relay it to their own manager, and so on until the final product makes its way back to you, the CEO. This is similar to how recursion works. A problem is divided into smaller subproblems until it is small enough to be solved directly. The concept of a function calling itself is like a manager in our analogy where they delegate a task to an employee. The employee will then give back or return their completed task so the manager can do whatever they need to do. If the manager is still unable to complete the task, it will be delegated to their own manager, and so on until the task is completed. In this manner, the function can solve the problem by repeatedly breaking it down into smaller subproblems until each subproblem is small enough to be solved. We often hear that computer science and mathematics are closely linked, so let's take a look at the mathematical foundation of recursion. We can take, for example, the Fibonacci sequence. In this sequence, the first two numbers are base cases. To make it easier, we'll refer to the position of the numbers as indices in an array. We always know that the number at index 0 is 0 and the number at index 1 is 1. After that, each number is the sum of the two previous numbers before it. For the number at index 2, we need 0 plus 1, which gives us 1. For the number at index 3, we need 1 plus 1, which is 2. For the number at index 4, we need 2 plus 1, which is 3, and so on. To write this out mathematically, we can write the base cases as f of 0 equals 0 and f of 1 equals 1. Here, f is the name of the Fibonacci function and the number between the parentheses is the index in our example. To get the recursive case, we write f of n, using n to represent the index or nth Fibonacci number, and make it equal to f of n minus 1 plus f of n minus 2, finding the sum of the two previous Fibonacci numbers. Notice that with the recursive definition, to compute something like the value at index 5 of the sequence, we would write f of 5 equals f of 4 plus f of 3. We need to first find f of 3, which is f of 2 plus f of 1. We know that f of 1 is 1, so we can substitute that in, getting f of 3 equals f of 2 plus 1. We now need to find f of 2, writing f of 2 equals f of 1 plus f of 0. We can then sub in the base cases to get f of 2 equals 1 plus 0, which means f of 2 equals 1. Notice that if we actually look at the sequence, we can see the item at index 2 is indeed 1. Now substituting that back into f of 3, we get f of 3 equals 1 plus 1, so f of 3 equals 2. Checking the value at index 3 of the sequence, we can confirm it's 2 as well. Now substituting that back into f of 5, we have f of 5 equals f of 4 plus 2. As practice, try to finish finding f of 5 by tracing through f of 4 the same way we've done for f of 3. Now let's talk about mathematical induction, which is a way to prove that a mathematical statement is true, typically for all positive integers. Induction is a two-step process where we start with proving that the statement holds for a base case. Secondly, we show that if the statement is true for a number, which we proved it is with the base case, it must also be true for the next number. Generally, to solve this mathematically, we would use algebra, but let's apply induction to our work delegation analogy. The base case would be to prove that the final employee has the skills and resources to complete their task directly. The inductive step would be the process of showing that if the task can be delegated successfully to one employee, it can also be delegated successfully to the next employee. Mathematical induction is beyond the scope of this course, but it is a very useful technique that you are likely to encounter in your studies. In this video, we explored the fundamentals of recursion and how it is deeply rooted in mathematics. We learned about the base case and the recursive case and how they work together to solve problems in a more elegant and concise way. Overall, we can see that recursion is a powerful tool that can simplify complex problems and lead to more efficient solutions. By breaking down a problem into smaller subproblems, we can create a recursive algorithm that can solve the problem as a whole. In the next video, we will dive deeper into recursion and explore the call stack in the context of recursion. We will examine how the call stack works and how it can be used to better understand recursion. See you there!